Earth is a miracle. It is a tiny, wet, blue marble hanging in a cold and indifferent void, providing us with everything we have ever known. But miracles are fragile, from wandering asteroids to our own messy tendencies. There are 1,000 ways for our only home to become, well, less of a home. If we want to ensure that the story of humanity doesn't end with a whimper on a single planet, we need a backup. We need a plan B. And when we look out at the neighbors, one red dot stands out above the rest. Mars. It is the most Earth-like place in the solar system. But that is like saying a desert is the most ocean-like place because it has sand. Today, we are going to simulate the most ambitious engineering project in history. We are going to fix a planet. We are going to turn the red wasteland into a green, breathing world. But before we start dreaming of Martian forests, we need to look at the scoreboard. And right now, the scoreboard says we are probably going to die. Welcome to the despair dashboard. To understand how to fix Mars, we have to understand just how broken it is. First, let's talk about light and heat. Mars is about 5 times further from the sun than Earth is. This means it only gets about 43% of the sunlight we do. Imagine a permanent, chilly late afternoon that is high noon on Mars. Because of this, it is unbelievably cold, while a nice summer day near the equator might reach 20 degrees Celsius. The average temperature is a bone-chilling -62. In the winter, at the poles, it can drop to -153 degrees. At that point, the air itself starts to turn into dry ice and fall as snow. On Earth, we worry about a 2-degree change in climate. On Mars, the climate is trying to turn you into a human popsicle every single night. Then there is the gravity. Mars is a small world. With only about 38% of Earth's gravity, this sounds fun at first. You could jump over a house and feel like a superhero, but for your body, it is a slow disaster. Without the constant tug of Earth, your bones get brittle and your muscles start to wither away like old grapes. We don't actually know if humans can stay healthy for decades in 0.38 G because we have never tried it. If we want to live there forever, we might just have to accept that we will become a different, taller, and much more fragile version of ourselves. But the real killer, the thing that keeps planetary scientists up at night, is the pressure. Mars has a surface pressure of about 6 millibars. For context, Earth is at 1,000. That is less than 1%. On Mars, the atmosphere is so thin it is practically a vacuum. This brings us to the Armstrong limit. If you stepped outside on Mars without a pressurized suit, the boiling point of water would drop below your body temperature, your saliva, your tears, and the moisture on your lungs would literally boil away into gas instantly. It wouldn't be like an explosion in a movie, it would just be a very quiet, very terrifying way to stop existing. And what little air is there? It is 95% carbon dioxide. To a human, CO2 is not just unbreathable, it is toxic. Even if you had a magic pump to increase the pressure, you would still suffocate in seconds. Plus, there is no magnetic field. Earth has a giant magnetic shield that deflects the sun's radiation like a cosmic umbrella. Mars lost its umbrella billions of years ago. Now, the solar wind is constantly sandblasting the top of the atmosphere into space, while high-energy radiation rains down on the surface, ready to shred your DNA. But wait, it gets even worse. The very ground you would stand on is a toxic trap. Martian soil is laced with perchlorates, nasty salts that are used on Earth as rocket fuel. If you got this dust on your suit and tracked it into your habitat, it would eventually wreck your thyroid and make your blood feel like it is made of lead. It is like trying to build a playground in a massive pile of industrial bleach. To make Mars livable, we don't just need to add things, we have to scrub the entire planet clean of its own poison. It is a world of dust storms, toxic soil, and silence. But there is a tiny glimmer of hope. Mars used to be different. We see ancient riverbeds, dried up lakes, and giant deltas. This planet used to have thick air and splashing waves, and the ingredients are still there. We have found massive deposits of water ice at the poles and buried just beneath the red dust. We have all the carbon and nitrogen and minerals we need locked in the rocks. The planet isn't dead, it's just in a deep, frozen coma. To wake it up, we have to solve 3 massive challenges in a specific order. We can't breathe if we aren't warm, and we can't get warm if we don't have a way to build. So, our journey begins with Challenge 1, the industrial foundation. The problem is a classic chicken and egg nightmare. To terraform Mars, we need a massive amount of machinery. Think thousands of factories, mirrors, and atmospheric processors. But to build those things on Mars, we need people and resources. And to have people on Mars, we need terraforming. We are currently stuck at 0. Right now, sending a single kilogram of stuff to Mars costs more than its weight in gold. If we try to ship our terraforming kit from Earth, We will go bankrupt before we even land a screwdriver. We need a way to build a planet-sized project without the planet-sized price tag. Some people suggest option A, the Great Conveyor Belt. We build everything on Earth, put it on giant rockets, and just keep launching until Mars is full of shiny toys. But the physics simply doesn't work. The sheer volume of material needed to change an entire atmosphere is millions of times more than all the rockets in human history could ever carry. It would be like trying to fill a swimming pool by carrying water in a thimble from 3 miles away, while the sun is trying to evaporate the water. It is slow, expensive, and one bad launch could set the whole project back by years. So, we switch to the option that can actually work, option B, the self-replicating machine. We don't bring the factories, we bring the things that build the factories. This is called In-situ resource utilization, or ISRU. On Earth, we are already getting pretty good at this. We have 3D printers that can build houses out of concrete, and robots that can mine deep underground without a human in sight. To make this work on Mars, we need to upgrade these systems to handle the Great Red Nothing. We need robots that can survive the dust, eat the Martian regolith, and turn it into steel, glass, and solar panels. Is this actually feasible? Surprisingly, yes. NASA has already proven the basic principle with a toaster-sized device called MOXIE on the Perseverance rover. It sucked in the thin Martian air and successfully squeezed out pure oxygen. It was a tiny baby step, but it proved the physics. If we can make oxygen, we can make fuel. If we can make fuel, we can power the miners. If we have miners, we have the world. First, we build what we need. Then we deploy it where it matters. Then we test it until it stops failing. Then we scale it up. And finally, we make it boring. The execution looks like a carefully choreographed robotic dance. First, we send a fleet of autonomous scouts to map the richest mineral deposits looking for iron, aluminum, and silica. Then we drop seed modules at the Martian equator. These are compact, rugged units containing a small nuclear reactor and a few highly specialized 3D printers. Once they land, the miners start chewing through the red dust, refining it into raw elements. The printers then use those elements to build more miners and more printers. Imagine it like a colony of ants. One ant can't do much, but a million ants can move mountains. We start with a few dozen machines, but within decades, the surface is crawling with millions of little metal workers, all humming with the same purpose. A literal tide of chrome sweeping across the red dunes, turning dust into the building blocks of a new world. Then, we deploy these drones to expand the power grid, laying down thousands of miles of solar film made from Martian sand. Then, we build massive atmospheric ovens that bake the rocks to release trapped gases. Finally, we establish a global network of automated manufacturing hubs that churn out the specialized gases and mirrors we will need for the next phase. This isn't just a construction site, it is an artificial biosphere in its infancy. A planetary scale heart that starts beating before there is even a body to live in it. But there are failure modes. Mars is not a friendly job site. A global dust storm could coat every solar panel in red soot, cutting off power and leaving our robots to freeze in the dark. The extreme temperature swings expanding and contracting the metal could cause mechanical joints to snap like dry twigs. If the AI managing the resource flow hits a logic error 300 million kilometers away from the nearest IT guy, the whole colony might just stop. We are building a nervous system for a planet, and any glitch could be fatal. Still, if we succeed, we turn Mars from a scientific curiosity into a giant, automated construction site. We create a routine infrastructure where robots build the foundation of a civilization, while we watch from the safety of Earth. We are no longer visitors, we are the managers of a world-sized factory. Ignoring the scale, the physics checks out. But how long does it take to turn a desert into a workshop? In the near term, the next 20 to 50 years, we can expect to see our first automated outposts and the first few tons of Martian-made oxygen. This is a high-confidence phase because we are already building the prototypes today. In the midterm, the next 100 to 200 years, we could have a self-sustaining industrial base that no longer needs anything from Earth. This is medium confidence territory. It depends on how fast we can master autonomous AI. By the long term, we aren't just building tools, we are ready to use them to change the sky itself. We have solved the how. We have the robots. We have the power. And we have the blueprint to turn Martian rocks into a global industry. We have unlocked the ability to manipulate the planet's resources on a massive scale. But there is a reason we are still wearing spacesuits. Challenge 1 gives us the hammer and the nails, but it doesn't give us air to breathe or a sun that stays warm. We have the industry, but the world is still a frozen vacuum. To fix that, we have to do something truly monstrous. We have to start a global greenhouse effect on purpose. The machines are ready, the power is flowing, but the real work is just beginning. Can we actually force a whole planet to sweat? if you want to see how we turn a frozen desert into a humid hothouse. Stay tuned for our next simulation.